So what exactly does mildly flammable mean?
Let's review what we know about flammability. Combustion requires three things: fuel, oxygen, and heat. Combustion has been described as an exothermic chemical reaction between a fuel, in this case refrigerant, and an oxidizer, in this case atmospheric oxygen, which produces light and heat. Removing any one of these eliminates the possibility of combustion. First, let's talk about safety from the fuel standpoint. Flammable vapors can only be flammable within certain concentration limits. The upper flammability limit is the highest concentration of flammable vapor that will burn. Above the upper flammability limit, the fuel will not burn. The lower flammability limit is the lowest concentration of flammable vapor that will burn. Below the lower flammability limit, the vapor will not burn. So if we keep fuel concentrations outside of these limits, we have effectively removed fuel from the combustion triangle. Next, let's consider safety from the standpoint of oxygen. We can't reasonably remove oxygen from the air around the equipment, but we can ensure there is no oxygen inside the equipment. The likelihood of a flammable mixture inside the system is quite low because the concentration of fuel would logically be way above the upper flammable limit. However, having no air in the system would ensure that no combustion could take place inside the system. If we keep air out of the system, we have removed oxygen from the combustion triangle, at least as far as the combustion inside the refrigeration system is concerned. We can keep air out of the system by purging lines with nitrogen during brazing, testing for leaks after installation or repair, and evacuating systems before opening charging valves or adding refrigerant. ASHRAE Standard 34 is where we get the refrigerant safety classification system we're all familiar with. Section 6.1.3, entitled Flammability Classification, states, "Flammability tests shall be conducted in accordance with ASTM E681, standard test method for concentration limits of flammability of chemicals," and then in parentheses, vapors and gases. So the flammability tests are conducted according to ASTM E681 standard. Flame propagation refers to the spread of a flame through a combustible environment from the point where the combustion is started. Both the ASTM standard E681 and the ASHRAE standard 34 use the term flame propagation. We have a tendency to read past terms that we are not familiar with and mentally substitute more familiar terms in their place. No flame propagation does not mean no flame. The word propagation essentially means spread. The term flame propagation means spreading of flames. When ASHRAE Standard 34 defines Class 1 as no flame propagation, they do not mean no flames. It just means the flame does not spread. So a refrigerant may burn but not spread and still be considered Class 1. R410A is a good example of a refrigerant that is in fact flammable, but is classified as A1 because its flame stays within the boundaries established by the ASTM E681 flammability test. Let's take a closer look at how this test is set up and how flame propagation is defined. This drawing illustrates how the test is performed. Air and refrigerant enter the flask through the tubes passing through the stopper. A magnetically driven mixer mixes the air and refrigerant. Electrodes also pass through the stopper. A high voltage arc at the electrodes provides the ignition. If the resulting combustion stays within the 90-degree arc shown here by the red lines, the refrigerant is determined to have no flame propagation. If, on the other hand, combustion travels further than the 90-degree arc shown by the red lines, the refrigerant is determined to have flame propagation. Here is a picture of an actual test apparatus. This is a 12-liter glass flask into which the test gas is injected. A magnetically driven mixer, shown at the bottom, mixes the gas and the air. Electrodes are located at 1/3 the height of the flask. They have a 1/4-inch gap which is energized with approximately 15,000 volts to provide an ignition source. They pass through a rubber stopper with a light spring load. The stopper will lift to relieve pressure to avoid exploding the glass flask. The test is conducted at 140 degrees Fahrenheit at a pressure of 14.7 psia, in other words, standard atmospheric pressure. Flame propagation is defined as any combustion that extends further than a 90-degree arc from the point of ignition, shown here by the 2 yellow lines. Flame propagation would look something like this. Note that the combustion cloud extends past the 90-degree yellow lines. If the combustion stays within a 90-degree arc from the point of ignition, as shown here, the refrigerant is said to have no flame propagation. Although this refrigerant did ignite, the combustion cloud stayed within the 90-degree arc. Here are pictures of actual tests from Chemours showing from left to right R410A, R454B, and R290. If you look carefully, you can see that the R454B combustion cloud extends just a bit past the 90-degree arc. Here is an excerpt of a video showing the flame characteristics of several flammable refrigerants, in this case R32. The person holding the hose and lighter will first light the lighter, then the person controlling the cylinder will crack the cylinder valve. Note that the sputtering flame starts at the flame produced by the lighter and does not travel backwards to the hose. When the tester extinguishes the lighter flame, the refrigerant flame also goes out. This is because combustion of A2L refrigerant does not produce enough heat to sustain its own combustion. You have already been working with a flammable refrigerant and didn't know it. Although 410A is classified as an A1 refrigerant, having an A1 safety designation does not mean a refrigerant will not burn under any conditions. Purdue University is an engineering school. They do a lot of work in the field of refrigeration. Here are 2 pictures from a paper entitled Auto Ignition of R32 and 410A Refrigerant Mixtures with Lubricating Oil. They tested the ignition of refrigerant alone and then the refrigerant with mixtures of POE. The picture on the left is a picture of 410A igniting when blown directly onto a hot plate of 1508 degrees Fahrenheit. The picture on the right is a picture of R32 igniting when being blown directly onto a hot plate of 1452 degrees Fahrenheit. Note that both of these pictures are of pure refrigerant, not refrigerant and oil. In fact, the safety data sheet for R410A tells us this material can ignite when mixed with air under pressure and exposed to strong ignition sources. I believe we struggle with the concept that flammability can be mild because of our two-state thinking. Something either burns or it doesn't. This leads us to equate any flame as being like something we already understand, the combustion of propane. Let me draw a comparison with something that people also often think of in a two-state manner. Boiling. Boiling is hot, right? Well, what about now? There are, in fact, degrees of flammability based on the lower flammability limit, the heat of combustion, and the flame velocity. It does not take much Category 3 refrigerant to form a combustible mixture, and when it does burn, it makes lots of heat. Categories 2 and 2L require more refrigerant to make a combustible mixture, and when they burn, they make less heat. The difference between Category 2 and Category 2L is the flame velocity. Category 2L refrigerants are slower advancing than Category 2 refrigerants. Here are the Category 2L requirements listed in imperial units. It takes more than 1/10 of an ounce per cubic foot to make a combustible mixture. When it does burn, it creates less than 8169 BTUs per pound. The flame speed is less than 3.9 inches per second. And there's a fourth characteristic that I believe is just as important, and that is that the 2L refrigerants have a relatively high minimum ignition energy. This slide from Chemours compares the ignition energy of an A3 refrigerant, R290, otherwise known as propane, to R32 and R1234YF. The energy is measured in millijoules, which is 1,000th of a joule. A millijoule is approximately 1/1,000,000th of a BTU. First, let's take a look at R290. 1 millijoule ignites the mixture with what looks like an explosion as a result. R32 requires 100 times as much energy, 100 millijoules, and the resulting flame is far less dramatic. R1234YF does not ignite even at 1,000 times as much energy, 1,000 millijoules. In fact, it takes over 4,000 millijoules of energy to ignite a combustible mixture of R1234YF. I think the best way to explain flame velocity is to show it to you. This video from Chemours ignites a combustible mixture of R32 in a glass tube. You can watch the blue flame front slowly travel up the tube.
So let's get over to the lab and take a look behind the curtain.
So here at the base, momentarily. For reference, that was approximately 6.7 centimeters a second.
To illustrate the difference between A2L refrigerant and A3 refrigerant, I'd like to look at some important characteristics of R32 and R454B compared to R290 and R600A. It takes 8 times more A2L refrigerant than A3 refrigerant to form a combustible mixture. It takes up to 600 times as much energy to ignite an A2L mixture as compared to an A3 mixture. When they do burn, the A2L refrigerants make only 1/5 the heat of combustion as compared to the A3 refrigerants. And finally, the A2L refrigerants have only 1/8 the flame velocity compared to the A3 refrigerants. Perhaps the best way to illustrate the difference between A2L refrigerant flammability and A3 flammability is to see them side by side and observe the differences. These two excerpts are from a video produced by some South Korean testers who posted it online. I want to stress that I do not recommend doing this. Since these folks have already done it and made a video of it, I feel no need to do it myself, and neither should you. On the left is R32, an A2L refrigerant, and on the right is R290, an A3 refrigerant. Note how quickly the A3 refrigerant lights while the A2L refrigerant sputters. Also note that the flame of the A2L refrigerant does not travel back to the hose while the flame of the A3 refrigerant travels back immediately. Finally, note how the A3 refrigerant continues to burn even after the lighter is removed, while the A2L refrigerant immediately extinguishes when the lighter is removed. There are many videos online showing techs trying to light A2L refrigerant, many of them failing. Note that the folks who could not get the refrigerant to light are flowing the refrigerant through an air-fuel torch. Because these torches are designed to aspirate enough air for more flammable gases like propane or acetylene, the torch design ensures that the mixture is well below the lower flammability limit by mixing in enough air to burn highly flammable gases.
Even the folks that succeed by lighting an oxyacetylene torch and placing the flame in the stream of refrigerant leaving a charging valve only get modest flames. AHRI Test 8017 was a test of potential ignition sources with A2L refrigerant. It was conducted in November of 2017.
Test 8017 tested the possibility of common household ignition sources igniting a potentially combustible A2L and air mixture. So they tested cigarette insertion, plugs and receptacles, light switches, hand mixers, cordless drills, friction sparks, hair dryers, toasters, hot plates, and space heaters, and none of those things would ignite a flammable mixture of A2L refrigerant and air.
So what did burn?
Candles burned, but they did not ignite a major combustion incident. Instead, the candle flame just became taller. At first, the butane lighter would not ignite the R32 flammable mixture. Then they increased the percentage of R32 in the mixture, and it did burn somewhat like a candle, as you see here. The household item that caused the most combustion was actually a match. Here you see a match and 4 different A2L refrigerants. In addition to a whole series of possible household ignition sources, they used an electrically energized hot wire. The advantage of the wire being better control. By carefully controlling the voltage across the wire, more precise data was collected regarding ignition temperature. This table shows some of the results of the hot wire testing. The first 3 tests with mixtures of around 50% stoichiometric mix would not ignite, even at over 2000 degrees. Tests closer to or at 100% of a stoichiometric mixture burned around 1450 degrees. 2 important takeaways from this are that the UL standard requires mitigation of flammable mixtures at 25% of the lower flammability limit, and code prohibits hot surfaces above 1290 degrees in the duct. While the AHRI 9007 test tested many different types of possible ignition, the AHRI 9008 test tests specifically hot surface ignition temperature for A2L refrigerants. It was conducted in November of 2017. One of the most common concerns about A2L refrigerant is the possibility of ignition from strip heaters. This is also fairly logical, so AHRI tested it in their 9008 test. They took a 1.5 ton ducted fan coil with 15 kilowatts of electric heat, jumped out all the limit switches, and ran varying airflows from 115 CFM to 775 CFM across the strips. In one of the tests, the strips got up to 1700 degrees. They leaked out refrigerant at a rate of 12 to 18 pounds per minute and did not get any ignition. My reference for this information is an article in AHR News on October 23, 2020, where they're interviewing Dick Lord of Carrier. Another obvious potential ignition source would be the pilot light on a gas water heater. So they took an old gas water heater, not one with a flammable vapor ignition resistant technology, and they built a stoichiometric cloud down near the base of the water heater where it pulls in its combustion air. The pilot flame did react, it got longer, but there was no combustion outside the water heater. In other words, the pilot light did not light the vapor that was accumulated at the base of the water heater. Again, my reference for this is the AHR News article on October 23, 2020.
Let's recap what we've learned about A2L refrigerant. It takes a higher concentration of refrigerant to form a flammable mixture. It takes more ignition energy to ignite that mixture. It produces less heat if it does burn, and it burns far slower when it burns. As a result, A2L refrigerant will not sustain its own combustion.
Hi, this is Carter Stanfield, co-author of Fundamentals of HVACR. I hope you enjoyed this presentation. If you did, please consider buying my book. You can find it online at Fundamentals of HVACR, 4th edition, published by Pearson, authors Carter Stanfield and David Skays.